Well, we're approaching the end of this lecture course, and this is our last theme, Theme 8, and I've called it Returning Home. It picks up on the notion I introduced in the first lecture that this course is a bit like a journey. We started close to home with the historical roots of cosmology, and since then we've been travelling, sometimes very far from home or very far back in time. But now at the end of the course, I want to take 3 lectures to bring us back home to our human world and look at how some of the cosmological themes we've been talking about might be more directly relevant to us. We're going to look at rather different topics. Next lecture, we're going to see what the next decade or two will bring in cosmological research, what key areas we're likely to make progress in. And in the last lecture, I want to look at a couple of really very different points. One is to ask why it is that we can actually understand the universe. And the other is to ask whether the modern cosmological story that you've just heard in these lectures can, or even should, take on the same psychological and poetic role that traditional creation myths often do. But in this first lecture, I want to develop a theme we touched on last time, which is to understand why the universe has the particular properties it does, the particular laws of physics, if you like, and not some other, quite different laws. Now, you might think that this is a question firmly set within physics, and although that's partly true, it turns out that we humans also enter the discussion in a rather interesting way. So let's begin by first looking at exactly what gives our universe its character. What determines the way things in it behave? The most obvious answer, of course, would be the laws of physics. Here they are, things like Einstein's relativity and quantum mechanics, the various conservation laws, the conservation of energy or momentum or charge, the 4 forces of nature, strong, weak, electromagnetism and gravity. And then there's the whole Standard Model with its various particles, fermions and bosons, leptons and quarks. All these really frame how everything behaves. From the tiny to the gigantic, everything follows these laws. But in addition, these laws often have very important parameters or numbers that characterize them. Here they are. Basic to relativity and quantum mechanics are the speed of light and Planck's constant. These set the speed and scale at which relativistic and quantum effects become important. Next are the strengths of the 4 forces. Just look at how incredibly weak gravity is, or how much stronger the strong force is compared to the electric force. And then there are the 25 or so parameters of the Standard Model, but I've singled out just 2 of them here. The fact that protons are about 2,000 times heavier than electrons, and that protons are a tiny bit lighter than neutrons. Now here's another set of parameters that define the character of the universe. These are really cosmological parameters, perhaps rather than physics parameters. So first of all, we live in a universe with 3 spatial dimensions and 1 time dimension. Now you may not think of these as parameters, but one can certainly construct, at least mathematically, universes with 4 or 5 spatial dimensions. But our universe has just 3. The next set we're already quite familiar with, the famous omegas, that give the composition of the universe relative to the critical density. The most important of these is, of course, the total omega, 1.00, to within about 1% accuracy. So our universe's geometry is flat or Euclidean. And then we have the 5 components: dark energy, dark matter, atomic matter, light, and neutrinos. Lastly, a very important aspect of the universe's character is that on large scales it is smooth, but on small scales it's slightly rough. There's a roughness parameter, often called Q, that's about 10 to the minus 5, which is basically the amplitude of the patchiness on the microwave background. So taken together, the laws of physics and the parameters of physics and cosmology, these pretty much define what the universe is like, all the way from the distribution of galaxies to the fact that planets can have people. It's really quite extraordinary. Who would have thought that this little list of numbers and laws could lead to something so huge and rich? So it is important to look at these laws and parameters a bit more closely. And let's start by asking a couple of important questions. The first one is, why do the parameters have the values they do? And the second one is, how would the universe be different if the parameters were different? Well, it's very easy to answer the first question. We don't know. We have no idea why gravity is weak and why the strong force is strong, or why the particles have the masses they do, or why there are just 3 space dimensions, or why the various omegas have the values they do. Although we do have a theory, inflation, that explains why omega total is 1. So for the moment, we just have to take these numbers at face value. That's what they are. Now, what about that second question? To answer it, what we need to do is to use our knowledge of physics to imagine universes with slightly different parameters. What are they like? Now, just to spill the beans, we'll discover a remarkable fact. Change almost any of the parameters, even just a bit, and the resulting change to the universe means we would no longer exist. So let's look at a few examples of this rather delicate situation that we're in. So here's one possibility. What if the early universe had exact matter-antimatter balance? Perhaps the broken symmetry that allowed the 1 in a billion advantage of matter over antimatter never got broken. So with exact balance, all matter annihilates, and we end up in a universe that contains just photons, a universe of pure light. That's a big difference. No atoms, no stars, no people. What about changing the relative strength of the 4 forces? For example, if we turn up the strong force a bit, then all the protons in the minute-old universe combine. So there'd be no simple hydrogen left over to fuel long-lived stars, and no hydrogen to make water, for example. On the other hand, turn down the strong force a bit, and the deuterium nucleus is unstable. So there's no way to get to helium or any of the other elements. Once stars form, they just cool down into dense balls of hydrogen. And with no elements, there's no planets, and again, no people. What about changing gravity? It's currently amazingly weak, about 10 to the 36 times weaker than electromagnetism. Now, in fact, one could probably change gravity quite a bit, but not too much, and not too much would change. But what about making it 1 billion times stronger, so that it is only 10 to the 27 times weaker than electromagnetism? Well, in a universe with gravity this strong, and everything else the same, stars would contain about as much mass as a mountain, and would shine for just 1 year. Galaxies would form much faster and be much denser packed with stars, making planetary orbits vulnerable to disruption. Meanwhile, planets would be only 100 meters across, and any life forms larger than ants would be crushed. This would be a very rapidly evolving universe, so rapid that there probably wouldn't be enough time for chemical reactions to take the long road of evolution to make life. And again, we have a sterile universe. Well, what about changing particle masses slightly? There's a very delicate balance between protons and neutrons. Proton is just 0.2% lighter than a neutron. If their masses were reversed, with protons slightly heavier, then atoms would collapse because their electrons could now combine with protons to make neutrons. So the universe would just contain chunks of neutron matter. Now, on the other hand, if we make the neutrons, say, 10% heavier than protons, then even inside nuclei, neutrons would decay into protons, causing the nucleus to disintegrate and blow apart. So again, we have no stable atoms and no chemistry and no us. Now here's an interesting diagram. It shows the properties of universes with different numbers of space and time dimensions. This may seem a bit odd, but it's often possible to solve the equations of physics in coordinate systems with different numbers of space and time axes. You can see that almost all of the combinations of the number of space dimensions along the bottom and the number of time dimensions up the side yield shaded, sterile universes. The solutions yield chaotic, unpredictable, or unstable behavior, or they're just too simple with no richness. Only our combination, with 3 space and 1 time dimension, gives stable, well-defined behavior that is also rich in possibilities. What about inflation? Could that have been much different? For example, the roughness parameter, Q, that's about 10 to the minus 5 and was set by inflation. Well, if the initial roughness had been, let's say, 10 times larger, then much more massive structures would have formed much sooner and had been much denser. So rather than having galaxies and clusters of galaxies, we'd have huge black holes instead. And the energy released when they formed would heat any remaining gas to millions of degrees so that it couldn't cool to form stars. Now, on the other hand, if the initial roughness was set, let's say, 10 times less, then galaxies would form much later and would be much less dense. And if they were delayed too much, they'd never form, because dark energy kicks in and quickly stops any more structure formation. And with no galaxies, there's no recycling of elements, so there's no planets, and again, no people. Well, that's enough examples of alternate universes. Let's take stock of what we've just learned. It seems a rather interesting situation is emerging. The parameters of the present universe seem to be rather special. They seem to be fine-tuned in the sense that if they were much different, the universe would be sterile and lifeless. It's almost as if the parameters seem fine-tuned for life. Now, this rather striking and puzzling fact has come to be called the fine-tuning problem. The question is, why do many of the parameters of nature seem to lie in a narrow range that also happens to make the universe highly fertile? Now, there are a number of possible answers to this question, but I want to say at the outset that there's no single answer that's widely accepted. And in fact, there is often considerable and sometimes heated disagreement about the subject. So with that in mind, let's look at some of the possibilities. The first one is that as physics and cosmology progress, we will ultimately understand the origin of all of these parameters. And finally, it will become apparent that they could, in fact, have been no other way. They would have to have the values they do. We've already met an example of this sort of thing. Remember, before we had a theory of inflation, we had the flatness, horizon, and structure problems, which all suggested the standard hot Big Bang was very fine-tuned to give a flat, smooth universe. But the subject progressed, and the theory of inflation now explains that particular fine-tuning as a natural byproduct of an early accelerating expansion. So who knows? Perhaps when we go beyond the standard model, we'll know why the particles have their particular masses and why the forces have their particular strengths. They may simply have to have these values. Of course, one might still be puzzled why the particular theory was so unusually fertile, but perhaps that will also be apparent when we know it. See, here's a nice illustration of how a simple principle can lead to great complexity. Look at these two math formulae. The first one describes the circle, while the second one, which is only marginally more complicated, describes the famous Mandelbrot set. If you zoom into this graph, you find ever more complex shapes at ever higher magnification. They'd go on and on forever, but this movie stops after a magnification of 60 billion. If the first image was a meter across, the last one would be inside an atom. So who knows? Maybe a deep but simple principle of physics, a symmetry principle perhaps, yet to be discovered, automatically leads to the fabulously complex world that we live in. So that's one possibility. The other possibility, of course, is that at least some of these parameters could have been different. Somehow, during the Big Bang, this particular set of parameters emerged. Now, how this might actually happen we'll come to in a minute, but for now, let's just say there really was some flexibility in the parameters. So if we combine this possibility that the parameters could have been different with the fact that the actual parameters seem to be fine-tuned, then we're back with our puzzle. With so many sterile parameter sets to choose from, why did nature choose a very special, i.e. unlikely, life-giving parameter set? Now, there are three broad types of answer to this, so let's have a look at these. The most straightforward answer is to introduce a creator figure, a deus ex machina, who has the desire and the capacity to select a life-giving set of parameters. This will be a very interesting hybrid cosmological theory that has a metaphysical moment of creation, rather like traditional cosmologies, but then immediately moves into a physical, scientific account. Now, for some people, particularly those with a prior religious conviction, this makes the most sense. But there are some concerns. For example, the idea belongs to a well-known category that is often referred to as the God of the gaps, meaning when there is a gap in our understanding of nature, God is introduced to explain it. Now, unfortunately, the history of this line of reasoning has not been a good one, because in time, a natural explanation for the phenomenon is usually found and the gap goes away. But who knows? Maybe this is a higher order gap, creation itself. So maybe the gap will never go away. Another concern is that we've simply replaced one unknown with another. We may have explained the parameters of physics, but now we need to explain how the creator was created. So as an explanation, it's not clear whether we've made any real progress. Now, a second approach takes a rather different viewpoint. It begins with the following innocuous statement. Because we exist, the parameters must have values close to their observed ones. It's not that our existence somehow made the parameters what they are, it's just an after-the-fact condition. If we exist, then the parameters must have their life-supporting values, because if they didn't, we wouldn't be here asking all these questions. Now, this is called an anthropic explanation for why the parameters have their particular values. Even if nature allowed other kinds of universes, our presence means it must be a life-supporting universe. Now, there's nothing too controversial about that statement, but what is much more debated is how much further you can go with that line of reasoning. Here's the really difficult question. Should you still be surprised that such an unlikely parameter set arose? There's great disagreement on the answer to this, with two groups. No, you should not be surprised, and yes, you should be. So, those in the no camp tend to take a very strict statistical view. They say the following: let's not get confused between before the event probabilities and after the fact probabilities. These are more technically referred to as a priori and a posteriori probabilities. The situation is a little like being a newspaper reporter sent to interview the survivor of a shipwreck. The very fact that you've been assigned an interview means you are not in the least bit surprised to find the survivor. But the survivor probably has a very different perspective and feels extremely lucky to be alive. So while the survivor experiences the very low before the event probability of survival, you, the reporter, experience the very high after the fact probability of survival. And it's important to realize that in the cosmological context, we are the reporter, not the survivor. Now, this perspective also suggests you can't infer anything about the shipwreck. That's about the nature of the Big Bang. For example, even if you learn that surviving shipwrecks is extremely rare, you can't conclude that there were many people on the ship, or that there were many shipwrecks, or that there was divine intervention. That kind of inference is simply not available to you. All you can conclude is that there was a shipwreck and someone survived. End of analysis. All right, now let's turn to the view that there is still something fishy about living in a universe whose parameters are so finely tuned. Perhaps you learn that only 1 in a trillion parameter sets is life-giving, and you just can't believe that with those odds, the Big Bang managed to get that lucky. So you begin to wonder about a new possibility. Perhaps there were a trillion Big Bangs, and then it would not be surprising that at least one had life-giving parameters, and guess what? We'd be living in that one. Now, this particular perspective has become much more popular recently because of 2 important developments. The first we met last lecture, which is that chaotic and eternal inflation can both generate vast numbers of universes within a multiverse. And the second is that inflation and string theories both include mechanisms that can effectively set the laws of physics during the very early stages of a Big Bang launch. For example, in string theory, the laws of physics are created during compactification, when the higher dimensions curl up to make the tiny Calabi-Yau spaces. The best current estimates suggest there are enormously many possible ways in which this can happen, of which, presumably, only a small fraction yield life-giving laws of physics. And I'm sure you can see where this is all going. We can combine these 2 ideas. Inflation generates huge numbers of universes, which all have different laws of physics. Of these, most are sterile, but a few are life-supporting. Obviously, then, we find ourselves in one of these. And so anthropic reasoning explains why we have the parameters we do. So here's the ultimate situation. We have our multiverse with many universes. Here we are. Our visible horizon is a small part of our own life-supporting universe. Now we know that our laws of physics extend to the visible horizon because we observe distant galaxies with the same atomic spectra and chemical elements. But if we went much further, we may begin to cross into other universes where the laws of physics are different. Most of these would be sterile. For example, no matter, or only neutrons, or all black holes. Some might even be entirely separate spacetimes, with no part in common with ours. And then perhaps, occasionally, there will be another life-supporting universe, maybe even more fertile than our own. It's a very nice parallel here between finding ourselves in a very special life-supporting universe and finding ourselves on a very special life-supporting planet. If there was just one planet in the galaxy, and it was ours, this would seem fishy. But of course, it's no longer fishy as soon as you realize that there are billions of planets in the galaxy, most of which are sterile, although some are not. And of course, we find ourselves on one of these. Let me summarize. We started by looking at the relatively small number of laws and parameters of physics and cosmology. These make the universe what it is, from stars to galaxies and from chemistry to life. We then played an interesting game. we imagined changing the parameters slightly and found that most changes would result in a universe in which we humans would never have been created. So this was the fine-tuning problem. Why do the parameters have special life-giving values? There were several possible answers to this question. Perhaps a future theory of physics will find a deep principle that explains why the parameters have their values. Or perhaps a creative figure chose them because they wanted to create a life-supporting universe. We then looked carefully at the obvious anthropic argument that simply by existing, the parameters must have values in the narrow life-supporting range. Now, there is considerable disagreement how to interpret this. A strict, statistically minded approach says you cannot infer anything more. Our after-the-fact presence shuts down the interpretive process. But recent work on inflation and string theories suggests that there may be multiple universes, and each may have different laws of physics. And these provide a new explanation for the fine-tuning problem. In the same way that the Earth is a special planet amongst many sterile ones, perhaps our universe is a special one amongst many others. So it's not surprising that we find ourselves on a very special planet, nor that we find ourselves in a very special universe. Now, I don't know how you feel about this topic. Personally, I find it a little bit slippery and not altogether satisfying. But maybe in time, things will become clearer, as they so often do. Now, let me end with 4 quotes to show you the range of disagreement, even amongst physicists and cosmologists. So this is John Polkinghorne, Professor of Physics at Cambridge and Anglican priest. There is just one universe, which is the way it is in its anthropic fruitfulness, because it's the expression of the purposive design of a creator who has endowed it with the finely tuned potentiality for life. Now, this is Heinz Pagels, physicist and executive director of the New York Academy of Sciences. I would opt for rejecting the anthropic principle as needless clutter in the conceptual repertoire of science. This is Martin Rees, cosmologist and astronomer royal in Britain. Saying that our cosmic environment is well-tuned for our sort of life is not just a tautology. It yields genuine understanding. And finally, this is Steven Weinberg, Nobel Prize-winning particle physicist. My own best guess is that we are going to find that, in fact, all the constants of nature, with one possible exception, are fixed by symmetry principles of one sort or another, and that the existence of some form of life will turn out not to require any very impressive fine-tuning of the laws of nature. So if you weren't quite able to sort out the subject and come to a clear understanding, don't worry, you're in good company.